Good day and mabuhay. I am Kira Emmanuel B. Felix, and at this moment, I will be presenting the first unit in the topic of tangent functions, which is graphing the said function with a vertical stretching factor. We can modify the tangent curve by introducing vertical and horizontal stretching and shrinking. That is why, before we go on with this unit, we should first recall that the extended formula for the graph of the tangent function is given by f of x, or simply y, is equal to a times the tangent of b multiplied by the quantity of x minus c and then plus d. But since we are just graphing the tangent function with the vertical stretching factor, we can simply use the standard equation of the tangent function, which is y is equal to a times the tangent of the quantity bx. Because there are no maximum or minimum values of a tangent function, the term amplitude cannot be interpreted as it is for the sine and cosine functions. Instead, we will use the phrase stretching or compressing factor when we are referring to the constant a. As the name implies, the stretching or compressing factor, or a, is the factor that will vertically stretch or shrink our graph. Moving on to know if the graph will have a vertical stretch or will be compressed, we must get its value. Since the stretching factor of the tangent graph is represented by an absolute value of a, if a is greater than 1, the graph will have a vertical stretch by a factor of a. If a is between 0 and 1, the graph will be vertically compressed by a factor of a. If a is less than 0, the graph is either stretched or compressed and also reflected across the horizontal or the x-axis. Lastly, if a is equal to 1, no stretching or compressing will occur. Now is the time to apply our understanding. Let us graph the function of y is equal to 3 times the tangent of the quantity x.
Step 1 is to find the vertical stretching factor. In our function, we can clearly see that 3 is our a when compared to the standard equation of the tangent function, which is y is equal to a times the tangent of the quantity bx. This means that our graph will have a vertical stretch by a factor of 3.
Step 2 is to find the period and to find the pair of vertical asymptotes. We can find the period by identifying b in our given function. Since in the function, the coefficient of x is 1, we can say that b is equal to 1. Now to find the period, it is equivalent to pi over the absolute value of b, which in our case is 1, hence p is equal to pi over 1, or simply just pi. Therefore, our period in this case is pi. Moving on to find the pair of vertical asymptotes, we can do it so by solving the given equations, which are bx is equal to negative pi over 2 and bx is equal to pi over 2. Substituting the value of b, which is 1 to the equation, we would get x is equal to negative pi over 2 and x is equal to pi over 2. For that reason, we can say that these are a pair of vertical asymptotes for the given function. Step 3 is to plot the points of the graph. To get such points, we can restrict the domain to this specific cycle, which is x is greater than negative pi over 2 but less than positive pi over 2. From this, we now can locate such points. When x is negative pi over 4, y will be negative 3. When x is 0, y will definitely be 0 as well. And when x is equal to positive pi over 4, y will be positive 3, so on and so forth. Step 4 is to draw a continuous curve through the plotted points.
Step 5 is to find the other asymptotes. It is said that the asymptotes occurring at x is equal to pi over 2 multiplied by the absolute value of b plus pi over the absolute value of b times k, where k is an integer. After solving this, we now can get the various values of x, or also known as our asymptotes, which are negative 5 pi over 2, negative 3 pi over 2, negative pi over 2, positive 5 pi over 2, positive 3 pi over 2, and positive pi over 2.
Step 6 is to locate the other points. Since we have found the other asymptotes, it is now time to locate the other points. We can do this by substituting the value of x into the function, which would then give us the value of y. Just like when x is equal to negative 9 pi over 4, y would be equivalent to negative 3. Or when x is equal to negative 2 pi, y would be equal to 0, so on and so forth. Step 7 is to plot the remaining points and draw smooth curves. As seen on the image, this is the final and completed graph of the function y is equal to 3 times the tangent of the quantity x. I have also given the domain and range of the function, which is x such that x is not equal to pi over 2 plus pi times n for any integer n for the domain, and negative infinity to positive infinity, or simply all real numbers for the range. Now, comparing the graph of the function y is equal to 3 times the tangent of the quantity x to the graph of the parent function, which is f of x, or y, is equal to the tangent of quantity x. The graph of y is equal to 3 times the tangent of the quantity x is vertically stretched by a factor of 3 compared to the parent graph. This means that the graph of y is equal to 3 times the tangent of the quantity x will oscillate or fluctuate more widely between negative 3 and positive 3 compared to the parent graph, or y is equal to the tangent of quantity x, which oscillates or fluctuates between negative 1 and 1.
Now let's move on to graphing a tangent function with horizontal stretching. In the equation y equals a times tangent quantity b x minus c plus d, the value of b will determine by how much the graph will horizontally stretch or shrink. We will have to remember that the absolute value of b is inversely proportional to the period of the graph. This is because the period of the graph, or p, is equal to pi over the absolute value of b. It means the curve repeats itself every p radians. Now let's try to apply our understanding. We have the function y equals tangent to x. For the first step, we need to find the vertical asymptotes. We have x equals quantity of pi over 2b plus c plus n pi all over b. As n could be any integer, we can start by substituting 0 and negative 1 and get x equals positive negative pi over 4 as the vertical asymptotes. Second is finding the period, and as mentioned, it is by dividing pi over the absolute value of b. In the given function, b is already the absolute value, so we get p equals pi over 2. Now finding the domain and range means remembering two things. The domain is everywhere the vertical asymptotes are not, and the range is a set of all real numbers. Fourth step is plotting points from the graph. Here we have the origin, and from there, we evaluate positive negative pi over 4 times the absolute value of b to get positive negative pi over 8. We find out the values of y with these values of x, so the points are negative pi over 8, negative 1, 0, 0, and pi over 8, 1. We can now draw the curves of the graph, keeping in mind the vertical asymptotes, period, domain and range, and plotted points. The red curves make up the graph of our given function, while the blue lines are y equals tangent of x. As pi is only divided by 1, the period is longer compared to the half of pi of y equals tangent to x.
Mabuhay, I am Yorike Tabirara, and for this unit, I will present the tangent function with horizontal shift. But first, let us recall the standard form of the tangent function. In case of the horizontal shift, what we are dealing with is the phase shift. So c is equal to the phase shift. So phase shift is the distance of the horizontal translation of the function. To further deepen our understanding, let us look at both cases where c is positive and c is negative. So if c is positive, then it implies a transition to the right. Then if c is negative, it now implies a transition to the left. Let us deepen our understanding by applying what we have learned. So let us graph the function y is equal to the tangent of the quantity x plus pi over 2. So for the first step, let us find the phase shift. So as mentioned earlier, phase shift is equal to c. And from that we got negative pi over 2. So this implies that the graph or the tangent function, the original tangent function, will shift pi over 2 units to the left. So the first cycle begins at the 0 point, pi over 2 units to the left of the origin, and we mark it at negative pi over 2, comma 0. Next is we find the period and the asymptotes. So b is equal to 1, and from that we can get the period. So the period is equal to pi over b. Since b equals 1, then pi over 1 is equal to pi. Therefore, the asymptotes are located 1 half of p, which is pi over 2 units, to the left and right of x equals negative pi over 2, which are x equals negative pi and x equals 0, respectively. Next is we plot the points of the graph. So for now, let's restrict the domain to this cycle, which is x is greater than negative pi but less than 0. So let us locate this point. So if x equals negative 3 pi over 4, you will get negative 1, and so on and so forth. So after we plotted the points, let us draw a continuous curve to show the tangent graph on that particular domain. Now let us find the other asymptotes. So you can continue doing the process earlier, or you can use this formula to find the other asymptotes of this function. So when you are to use b is equal to 1, we will get these following asymptotes. So they are located at x equals negative 2 pi, negative pi, 0 pi, and 2 pi. Now let us locate the other points of the tangent graph. So I've decided that the domain of this function would only be from negative 2 pi to 2 pi. So from that, we locate these points, their corresponding x and y values. So after we got those points, we plot the remaining points and draw smooth curves on them. So on the right, we get the resulting graph of the function tangent of the quantity x plus pi over 2. Also provided on the left are the information on the domain and the range of the said function. Now, let us see how the horizontal shift changed the graph of the original function. So as mentioned earlier, when we graph the function y is equal to the tangent of the quantity x plus pi over 2 compared to the original function, which is y is equal to tangent of x, we can see that the graph has shifted pi over 2 units to the left.
Mabuhay! I am Jamil Pama, and for Unit 4, I will be graphing a function with vertical shift. This is the standard form of the tangent function. So what is the vertical shift? The vertical shift is the amount by which a trigonometric function is transposed along the y-axis, or in simpler terms, the amount it is shifted up or down. It is usually represented with the letter d. If d is positive, the graph shifts upward. If d is negative, the graph shifts downwards. Here we have a sample problem. Y equals tangent x plus 2. We will be graphing this tangent function. The first step is to find the vertical shift. If we look at the problem, we can say that the vertical shift, or d, is positive 2. This implies that the graph will shift 2 units upwards from the starting point, which is y equals 0. The next step is to find the period and the asymptotes. B is equal to 1. Period is equal to pi over the absolute value of b, which in our problem is equal to pi. Therefore, the asymptote is located on the pi over 2 units to the left and the right of x equals 0, which are x equals negative pi over 2 and x equals pi over 2 respectively. The next step is to plot the points in a graph. In this specific cycle, the domain is negative pi over 2 is less than x is less than pi over 2, or x is in between negative pi over 2 and pi over 2. If x is equal to negative pi over 3, then our y will be negative square root 3 plus 2. If x is 0, our y is 2. If x is pi over 3, then our y will be square root of 3 plus 2. On the right hand side, we can see the points and where it is plotted. The next step is to draw a continuous curve based on the points that we have plotted on the previous step. The next step is to find the other asymptotes. The asymptotes occur at x equals pi all over 2 times the absolute value of b plus pi over the absolute value of b minus k, where k is an integer. For our problem, the asymptotes are x equals negative 5 pi over 2, x equals negative 3 pi over 2, x equals negative pi over 2, x equals pi over 2, x equals 3 pi over 2, and x equals 5 pi over 2. The next step is to find the other points. We can do this by substituting x. Let's start with negative 7 pi over 3. If this is the case, y will be negative square root of 3 plus 2. If x is negative 2 pi, y is to 2. If x is equal to negative 5 pi over 3, y will be square root of 3 plus 2. If x is negative 4 pi over 3, y will be negative square root of 3 plus 2. If x is negative pi, y is equal to 2. If x is negative 2 pi over 3, y is equal to square root of 3 plus 2. If x is negative pi over 3, then y is negative square root of 3 plus 2. If x is equal to 0, y is equal to 2. If x is pi over 3, y is square root of 3 plus 2. If x is 2 pi over 3, then y is negative square root of 3 plus 2. If x is pi, y is 2. If x is 4 pi over 3, y is equal to square root of 3 plus 2. If x is 5 pi over 3, y is equal to negative square root of 3 plus 2. If x is 2 pi, y is 2. And if x is 7 pi over 3, y will be square root of 3 plus 2. Step 7. Plot the points from the previous step and draw smooth curves based on the points. The domain for our example is x such that x is not equal to pi over 2 plus pi times n for any integer n. And our range are all real numbers. By plotting a blue graph without a vertical shift, we can see how adding a vertical shift can affect the graph. Since our vertical shift is positive 2, then we can see that the graph shifted upwards of 2 units from y equals 0.
Good day and mabuhay. I am Melvin Luis Festin of 11 Leeuwenhoek, and today I will be presenting to you the tangent functions graphed with stretching factor and period. But first, let us first have a quick recall on the general equation of a tangent function. The general equation is y is equal to a tangent of b, quantity x minus c plus d. For my given equation, a is the stretching factor. First, what is the stretching factor? The stretching factor of a tangent graph, typically represented by an absolute value symbol, is a multiplier that determines the vertical expansion or compression of the graph compared to the standard y tangent of x function. It basically says that this function is stretched x units from the x-axis or n units from the x-axis, giving it stretch and making it deeper. Next, we have the period. The period is represented by pi over d. And given b, the period of a trigonometric function is the horizontal distance over which the curve travels before it begins to repeat itself. For the tangent functions, it is the amount of distance between asymptotes as well. But first, let us take into consideration if a is positive or negative. If a is positive, the direction of the graph is preserved and it makes the graph taller and deeper as it is increased. it is stretched vertically. However, if the quantity of A is negative and it increases in that, it causes the graph to change direction vertically while still preserving its period and stretching the graph vertically. However, it will be switched and reflected from its original positions. Now let us have an example. Let us graph the function y is equal to -2 tan quantity of 2x. First, let us find the stretching factor of the graph. The stretching factor is equal to the quantity of A, in this case is -2. This implies that the graph is to be reflected vertically as it is negative and is stretched 2 units away from the x-axis. The second step in finding the graph of a tangent function with stretching factor and period is to find the period and asymptotes. Given our b is 2, and to find the period it is pi over b, the period is pi over 2. Therefore, the asymptotes located 1/2 b is equal to pi over 4 units to the left and right of x equals 0, which are x equals -pi over 4 and x equals pi over 4 respectively. The next step in graphing the function, we have to plot the points of the graph. Given the domain of one part or one cycle, it is -pi over 4 to pi over 4. Now, we find a quantity that fits this criterion, which could be -pi over 8, 0, and pi over 8 as the x values. This can give us the y values of 2, 0, and -2 for this given cycle. The next step in graphing the function is to draw a continuous curve from the points plotted using the table of values. Once we have plotted one cycle, we will then find the other asymptotes. The asymptotes occur at x is equal to pi over 2 absolute value of b plus pi over absolute value of b, k, where k is an integer. We can find some other examples of asymptotes in this function, where x is equal to -5 pi over 4, -3 pi over 4, -pi over 4, 5 pi over 4, 3 pi over 4, and pi over 4. Once we have the asymptotes, we will then have to locate the other points. The other points in the equation are given below in the table of values, and we can use these as reference for the points that we will be using to graph our entire tangent function. Then, we will have to plot the remaining points and draw smooth curves from the points given that we found in the table of values. We will then know that domain is equal to x is an element of any real number, where pi over 4 plus k pi over 2, where k is an element of an integer, or k is an integer, and the range is from -infinity to infinity. Next, let's check the understanding of these following concepts. We know that by increasing or decreasing our period causes an increase in the distance between the vertical asymptotes in the equation, as demonstrated here in the function below. As you can see here, when we turn our stretching factor negative, it causes our graph to reflect or to switch sides vertically. However, it still preserves its period, and it still preserves all the qualities and all the characteristics of the original graph. However, it is now reflected. Again, this is Melvin Festin from Leeuwenhoek for graphing tangent functions with stretching factor and period.
Good day and mabuhay. I'm Honor Theodore C. de la Cruz of 11 Leeuwenhoek, and for our last unit, we'll be moving on to Unit 6. We're going to integrate the said parts and concepts said earlier to have a full graphing of the function and its needed parts. So to start, as discussed earlier, a tangent function has no amplitude. We have the equation y is equal to a tangent b times quantity x minus c plus d. We are given a, which helps us in finding the stretching factor. A is equal to the stretching factor. B, which helps us in finding the period, or pi over b is equal to the period. C, together with b, helps us in finding the horizontal shift or the phase shift. Hence, -c over b is equal to the phase shift, while d helps us in finding the vertical shift. Therefore, d is equal to the vertical shift. Provided here is a guide to deepen our understanding. For the value of a less than 0, the absolute value of a greater than 1, absolute value of a less than 1, and absolute value of a equal to the no stretch or compression.
For the b is the period or cycle of the tangent function, the distance between the repetition of any function. For c, if it is positive, it moves to the right. If it is negative, the transition moves to the left. And for d, if d is positive, the graph shifts upward. And if d is negative, the graph shifts downward. Now, let's have the example for graphing the function. Y is equal to 2 tangent times quantity 3x plus pi over 2 plus 1. The first step in graphing the tangent functions is to find the stretching factor and the period. To find the stretching factor, we have the absolute value of a, or absolute value of 2, which is equal to 2. And for the period, we have pi over b, which is equal to pi over 3, which is the period. Moving on to the next step, we find the phase shift, vertical shift, and the resulting asymptotes. The phase shift is equal to negative c over b, which will result in negative pi over 6, meaning pi over 6 units to the left. The vertical shift, on the other hand, is d, or simply d, which is equal to 1. It will shift up 1 unit. Then, we'll find the resulting asymptotes of the graph. Therefore, the asymptote is located at 1/2 of p, which is equal to pi over 6. Units to the left and right of x is equal to pi over 2, which are, so we'll simply add and subtract it to pi over 2, which will result in x is equal to pi over 3 and x is equal to 2 pi over 3 respectively. Step 3 is to plot the points of the graph. The domain of this cycle is pi over 3 less than x less than 2 pi over 3. Let us locate some points. The range of this function, or the range of this, is simply all real numbers. So to do this, to make the table of values, we simply plug in the values of x that are less than or greater than pi over 3 and less than 2 pi over 3. I choose the values 5 pi over 12, pi over 2, and 7 pi over 12. The resulting y values will be negative 1, 1, and 3. Step 4 is to simply draw the resulting continuous curve. Step 5. Find the other asymptotes. The asymptotes occur at x is equal to negative pi over 2 times absolute value of b plus pi over the absolute value of b, negative k, where k is an integer. The resulting asymptotes that I found were x is equal to negative 2 pi over 3, comma, negative pi over 3, comma, 0, comma, pi over 3, comma, 2 pi over 3, comma, pi, comma, 4 pi over 3, comma, 5 pi over 3. For the sixth step, we locate the other points. Now, as you can see, that's a table of values for the x values on the x-axis and the y values on the y-axis. We can see the pattern on the y-axis having the values negative 1, 1, and 3 only. And lastly, our step 7 is to plot the remaining points and draw smooth curves. Lastly, we have the resulting domain of the function and of course, the range of the function, which is all real numbers, or negative infinity and positive infinity. Here, to finally take a good look of the graph, here's the graph of the function y is equal to 2 tangent times quantity 3x plus pi over 2 plus 1, together with the mother function y is equal to tangent x, provided is the domain and the range being all real numbers as said earlier. You may take a good look at the graph, and I also provided and plotted the 13 points said earlier for easy visualization and graphing of the graph. That ends my Unit 6. Once again, I am Honor Theodore C. de la Cruz. Thank you and mabuhay!